So for number 1, we need to simplify it. Right now we got a square root in the bottom of our fraction. That means I got to rationalize the denominator. So I'm going to multiply top and bottom then of my fraction by that square root. So I multiply top and bottom both by root 2. 1 times root 2 on the top is just root 2. Root 2 times root 2 on the bottom, well, you might start by thinking of it as the square root of 4. But of course, the square root of 4 just equals 2. So that simplifies down to be root 2 over 2. That's what we're looking for there. All right, next up, for number 2, again, I need to rationalize the denominator, so I'm going to multiply top and bottom of this one by the square root of 5. When we do that, we end up with 30 root 5 all over 5. But you'll notice in this case, we're not done yet, because 30 over 5 reduces. I can divide both top and bottom of this fraction by 5. If I do that, 30 divided by 5 is 6, so that becomes 6 root 5. On the bottom, 5 divided by 5 is 1. Of course, anything over 1 is just itself, so we then say our answer is 6 root 5 there. And then for our last one, number 3, again we start by multiplying top and bottom by our radical. When we do that, we end up getting 16 root 20 all over 20. And again, we need to simplify it. But in this case, there's actually 2 layers of simplification that we need to do. One of them is that we can simplify and reduce the fraction like normal. I could divide top and bottom by the same value. But the other thing is that I can simplify my radical, simplify the square root. And I'm actually going to choose to do that part first. You technically can do either one first, but I'm going to simplify the radical first. Sometimes it saves me a step, so I like doing it that way. As a quick refresher here, remember if I start with a square root, if I want to simplify that square root, I look for either the biggest perfect square that multiplies into it, in this case that would be 4, or I make the factor tree, where you break 20 up into 2 numbers that multiply to it and keep breaking it down, and then you circle pairs, and any pair you circle is the number that's outside, and anything that's not circled is the number left on the inside. Either way you do it, you should get an answer here of 2 root 5. So our answer up here, I can now go and call it 16 times 2 root 5 over 20. Now some people get thrown off by the 16 times 2 root 5, but yes, we can go ahead and just multiply that like normal, so that's going to be 32 root 5. If you jumped straight to that step and you skipped this step in getting there, that's going to be okay. All right, but we still have to do the other part of the reducing here. What can I divide both 32 and 30 by?
20.
Not by 20.
No, 30.
I can divide them both by 4.
No, you said 30.
Did I say 30?
Yeah.
I misspoke then. 32 and 20. So 32 and 20 are both divisible by 4, so that's going to give me 8 root 5 over 5, because I divide both top and bottom by the 4. When I do that, 8 root 5 over 5 cannot be simplified or reduced anymore past that, so we're done. All right, now these problems are going to be coming up in some of our other work that we do today, including this problem. We're going to be simplifying this little fraction here. So please write down this fraction, and then we're going to go through the whole process about how we go about doing it. Now I know some of you, when this came up on the screen, you wanted to cry a little bit inside because it looked big and scary, but you know all the tools in order to be able to deal with it. It might look scary, but don't let a math problem intimidate you, or you'll psych yourself out thinking, yeah, I don't know how to do it, when in reality you can jump in and just start, and you'll find that you'll be able to do each step along the way. So like in this case, well, one of the things that looks scary about it is the fact that we have a fraction within a fraction. Well, we can change the way it looks then, so it doesn't look so scary. This fraction bar is the same as what operation? Division. Yeah, it's the same as division. So I can just rewrite that big old fraction instead as negative 1/2 divided by negative root 3 over 2. Now, every now and then somebody gets a little bit thrown off by the negatives there, so let's just be clear about what we do with the negative fractions. A negative out in front of a fraction, it means that either the top or the bottom of the fraction is negative, not both. Some people try to take that to mean that it's -1 over -2, but if it was, the negatives would cancel each other out. It'd be a positive then. So put it either into the top or the bottom. Personally, I like to put it up in the top just kind of as a matter of habit. And it means that I'm just nice and consistent and I don't get mixed up along the way. All right, but now I still have to do this division. Remember how we divide fractions? Came up in our recent work yesterday, didn't it? Dividing fractions is where we multiply by the reciprocal. Now, when I say multiply by the reciprocal, I'm saying the original multiplies by the reciprocal of the second fraction. So it's going to be looking like this. Notice, it's all one move, all one line, where I change the division into multiplication, and I do the switching where top becomes bottom and bottom becomes top. That is not two separate lines. Now that I'm here, I can go ahead and do the multiplication. Multiplying fractions, of course, is straight across the top, straight across the bottom. So on the top, I do -1 times 2, which of course is -2. And on the bottom, 2 times -3. Remember, that's 2 times -3, not 2 minus square root of 3. 2 times the square root of 3 is just 2 times the square root of 3. So this is where we've ended up so far now. We have -2 over -2 root 3. Now, I could start rationalizing the denominator right now. That'd be fine, but there's some reducing to be done, and it's kind of bugging me that it's there to be done. I really want to deal with it, so I'm going to deal with it. Notice what I can take out of both top and bottom, the -2. If I divide top and bottom by -2, what is left on the top? 1. Don't forget about the 1 there. So the root 3, it's still in the bottom. Now notice, this is our answer, but it's not quite formatted right, is it? Why did we do those first few problems at the start of class? Because we need to be able to do this type right here. So we got to rationalize our denominator. So we multiply top and bottom by the square root of 3. When you do that, we end up with the square root of 3 over 3. That can now not be simplified anymore past that. And so that is done. That is your final answer. All right, now keep this work handy that you've written down for this problem, because it's going to be coming back, as you'll see. But why are we doing that problem? Because it's going to allow us to do these as well. Today we are delving into tangents. We've looked at the exact values of sine and cosine so far. Today we're going to be looking at the exact values of tangent. Of course, you can get decimal approximations for tangent just by plugging stuff in your calculator, but just like sine and cosine, there are certain exact values we should know. Now, before we go too much further with this, you'll notice I wrote these two problems differently. This one without parentheses, this one with parentheses. What do the parentheses change about it? Absolutely nothing, actually. Whether we write the parentheses in or not, it means the same thing. So which one is better is usually the next question that I end up getting. My suggestion to you would be include the parentheses. Leaving out the parentheses is basically mathematicians being a little bit lazy, being a little bit sloppy. Putting in the parentheses, it's better to be there because remember, tangent is a function. And function notation has those parentheses in there. That's why we have these parentheses, because basically that's telling us what gets plugged into our function there. And so yes, the parentheses are better to be in there. Just realize that depending on who's writing the problems, writing your textbook, whatever it is that you're looking at, you might see it written either way. All right, so we're going to be tackling now how to find tangent exactly. In order to do that, I got to step back from these two problems for a moment and look again at our unit circle and our original definition of tangent. Tangent, of course, as you may recall, equals opposite over adjacent. Seeing that in my unit circle here, notice my opposite, that's how far I'm going up. My adjacent, that's how far I'm going over. But recently, we've been seeing that in the unit circle specifically, I can calculate the opposite and the adjacent with some of our other trig functions, right? What would I use to calculate the opposite? Sine, exactly. The opposite can be found just by doing sine of the angle. And the adjacent is cosine. And so sine is the opposite length. Cosine is the adjacent. Notice it's the x and the y basically. And in case you're wondering, no, tangent is not the hypotenuse, because the hypotenuse is 1. It's a unit circle. All right. So what does this do for me then? Well, notice the sine is the opposite. Cosine is the adjacent. So if I plug them in, we can see that then tangent equals sine over cosine. And yes, this would be good to put into your notes. And even taking this a step further, I was able to conclude this in the unit circle because, of course, in the unit circle, where our radius is 1, sine is the y value. And that's specific to the unit circle. But this ratio, because sine is the opposite over hypotenuse, and cosine is the adjacent over the hypotenuse, if we actually went through and did the math there of dividing those out, we'd find the hypotenuses would cancel each other out. And that tangent equals sine over cosine, not just in the unit circle, but all of the time. Tangent always will equal sine over cosine. So then, going back to the problems that we started with, tangent of 135 degrees, we now have a way to figure that out. Because we have a lot of notes, including this table, which I suggest you have out in front of you so you can use that as a reference. Keeps you from having to squint at the screen here. We can use the sine and cosine values that are already in that table to figure out tangent of 135. So to do that, tangent, of course, is sine over cosine. So I go to 135 and I see what is the sine value. And I grab that. The sine at 135 is root 2 over 2. That is going to be over my cosine value. So again, I go over to 135 and look to see what is cosine there. And you can see that it is negative root 2 over 2. That's how we can set it up. So now it's just a matter of figuring out what is root 2 over root 2 over 2, which sounds kind of scary when we say it out like that and just kind of look at it symbolically, but actually it's really easy. Because, of course, we're dividing root 2 over 2 by negative root 2 over 2. It's basically divided by itself. What is anything divided by itself? 1. And a positive divided by a negative is a negative. So it's negative 1. I didn't even have to do a whole bunch of fancy math work on this one. I could just look at it and know. Now, could you go and do it the long way? Yes. And if you really want to, you are welcome to. I didn't want to, so I didn't. All right, from there, let's take a look now at 210. So for 210 degrees, I'm going to do the same thing. I'm going to do sine over cosine. So I grab the sine value, which is negative 1/2. That's going to be over cosine, which is negative root 3 over 2. All right, so in this case, I have to do negative 1/2 divided by negative root 3 over 2. What does that equal? It's root 3 over 3, which is not some incredible feat of mathematics. We already did that. Remember, we took it as division, and we just worked that through. This is the exact same work that we saw and did earlier. One of the neat things about some of these tangent values is there's actually only a couple different calculations that you have to do. And once you've done those few calculations, you can just apply it to other problems. All right, so having seen those two, if I can go ahead and fill those into my table, so I know 135 now has a tangent of negative 1. Fill it in. Tangent of 210 degrees is root 3 over 3. What I'd like you to do now is fill in all of the rest of those values. I'm going to give you just a couple minutes because you only need a couple minutes. Fill in all of the rest of those tangent values. And I know some of you are thinking I was crazy when I was saying that you should only need a couple minutes. There's actually only one algebraic problem. Actually, technically it's arithmetic. But there's only really one bit of math that you're going to have to do here where you're going to have to write out any work. All the rest of it you can do in your head. Use that to your advantage here. Look for, why would you only need to do one thing? How can I reuse stuff I already know? Things like that. Now that one problem that you would actually have to show the work on is this one. Root 3 over 2 divided by a half. When you do that, it should give you just the square root of 3. Now there's no more actual real math to do. All of it now is just using what we know. All right, so I did that work and I found out that root 3 over 2 over 1/2 is just root 3. Now let's see how I can go ahead and now use that information to find out other stuff. So you notice that came from root 3 over 2 divided by a half. That root 3 over 2 divided by a half comes up again and again. The only thing that's changing is the signs on it, the positives and negatives. So I know that division is always going to be giving me the square root of 3. The only question about it is whether it gives me a positive or a negative root 3. For this one, of course, positive divided by positive is positive. Here, we're doing a positive divided by a negative. That's negative then. Here, we're doing negative divided by negative. That's positive then. And here, we're doing negative divided by positive. That'd be negative. Notice, 4 for the price of 1. I did one calculation. I was able to fill in 4 different items. We can actually go back and do the same thing with the very first one of these calculations we did to get the root 3 over 3. Anything where we're doing the 1/2 over the root 3 over 2. I'm going to be able to reuse that calculation there. And so all of those are going to end up being root 3 over 3. It just is a matter, though, remember, of checking what the signs are going to be. So positive divided by positive is positive. Positive divided by negative is negative. So I make that one negative then. So very good, negative. Let's try that again. There we go. This one is positive because it was negative divided by negative. And then negative divided by positive, of course, is negative. Basically, when doing those divisions, if the signs are the same, it's positive. If the signs are different, it's negative. All right, and so we can keep going with the same thing, like the root 2 over 2's. Well, remember, anything divided by itself equals 1. So all of those are going to be 1s. Just a matter of checking the sign again. So that last one ends up being negative. So notice, I didn't really need to do any more math. There's really only 2 math problems there where we had to put in work. And that was to get the root 3 over 3 and then to get the root 3. Those were the only 2 actual math problems we had to do. From there, it's just using math facts. Now you might be wondering, though, what about those other blanks that we haven't filled in yet? Again, use your math facts. Can we do 0 divided by 1? Yes, you can. If you have nothing and you cut it up into a bunch of pieces, you can do that. It's just that each piece is nothing. You know, you can think of it as if you have no money, but you're so gracious as to share it with all your friends, everybody gets an equal share of nothing, which is nothing. Now, on the other hand, what if you have 1 divided by 0? Well, if you have $1 and you want to split it up into 0 pieces, can you? No, because if you have the $1, that's already a piece in itself. So we can't cut it up into 0 pieces. We can't make it become nothing. And so that is impossible. I'll often just put an X through that spot. Technically, it is no solution, or does not exist, however you want to say it. So notice we can do 0 divided by a number, but not anything divided by 0. Which means 0 divided by -1 is 0, -1 divided by 0 does not exist, and 0 divided by 1 is 0. Take a moment, check all of your values for tangent here with a special emphasis on making sure that you have the negatives correct on all of them. All right, now having filled in all those tangent values, there's actually one more piece of this table that we are going to fill in, which might seem odd because you probably think that everything is filled in. It doesn't look like we got any empty spaces, but there is an awkward gap at the top, isn't there? We're going to be taking a look at another way to measure angles today, radians. So please start by adding this into your notes. But like most mathematical definitions, it can sometimes seem a little fuzzy at first. So I want to make this a little bit more concrete. First of all, this is a different way to measure angles. It's basically just a different unit for measuring angles. But really, it's also a different mindset for how to measure an angle. Because when we measure degrees, basically what we're doing is we're taking a look at the two radii of our circle, and we're looking to see how far apart are those two radii as they meet in the center of the circle. Radian measures are different. Radian measures are the length of the arc around the unit circle. So basically it's a measure around the outside of the circle instead of a measure on the inside. All right, now they both can still represent the exact same thing. So for instance, this can still represent the angle in degrees here, but it also represents the angle that gets traced out around the outside. Okay? Now, what is 1 radian going to mean then? Well, actually, 1 radian is kind of an awkward idea. And I want to show you why. First of all, how many degrees are in a circle? 360. Okay? We need to figure out what the radian equivalent is. So I need to figure out what is the length of the arc that gets traced out if I go around the entire circle. Well, if I go around the entire circle, it's no longer an arc. It's a circle. What do we call the distance around the outside of a circle? Circumference. And how do we calculate circumference? 2 pi r. The pi r squared one is area, for those of you who are thinking of that one. Now, this is a unit circle, right? What is the radius of our unit circle? The radius of a unit circle is 1 unit. And so then the circumference of my unit circle is just 2 pi. So in other words, my 360 degrees around a circle is equivalent to 2 pi radians. Those represent the exact same value. Now notice I did not write radians in as my units. Well, you know how for all these years, whenever you've used degrees, you've had to actually write the degree symbol? That's because when you're talking about angle measures, if we don't write it in, it's assumed to be radians. And so without the degree symbol, it means you're in radians, which is why it's always been such a big emphasis to make sure you do have the degree symbol in there. Now, why do we care about radians? Radians basically are the default for measuring angles. You know, there's no units with it because it's assumed that unless you state otherwise, you're working in radians. It's slightly more useful in some ways because you'll notice radians actually mean something about the circle. Like 2 pi radians is how far around the circle it is, or whatever your angle is. It's how far around the circle you went. What's the significance of a degree? There isn't really one, right? We just arbitrarily chose to cut the circle up into 360 pieces. So a radian at least has some actual significance when it comes to something physical. So it can be rather convenient that way as well. One other little note here before I give you some other formal notes. 0 radians is in the exact same place as 0 degrees. We still start measuring from the same place, horizontal right. Okay? Now, with that said and done, let's formalize the stuff that we were just talking about. So add this to your notes on radian measure. All right, now as you're finishing writing some of these down, you notice there's one additional thing, which we kind of have talked about and kind of not, which is this formula down here. And you've never seen it before yet I say you kind of have seen it. We've kind of talked about it already. Because, remember what a full circle was. A full circle in degrees is 360. A full circle in radians is 2 pi. So basically, if I'm going to be able to switch between the two, I'm just figuring out, okay, what fraction out of the whole 360 degrees is that? In other words, what fraction of the circle does that represent? And then I can use that to figure out the fraction of the other unit that represents out of the whole circle. Now, I will say that if you go and Google this kind of a formula, it's going to look slightly different. And yes, you can use a slightly different formula. It uses a 180 and a pi here instead. They try to simplify it a little bit. However, I don't like that one as much because we forget what it means. I find this formula much easier to remember because all you got to do is remember it's the number of degrees out of 360. In other words, a whole circle. And the number of radians out of 2 pi. Again, the whole circle. We're now going to actually do some of these unit conversions and see what does 135 degrees, for instance, look like when we convert it into radians. So you write down the 135, and then we're going to be going through it together, showing all the work. It's a lot of little detail-y stuff that we need to make sure we nail down. And of course, I am going to be using the same formula. I'm going to be doing d over 360 equals r over 2 pi. The 135, is that d or r? It is d. D stands for degrees, so I plug the degrees in for d. The other way to see it is, since it's degrees here, it needs to be over the total number of degrees that are in the circle. As you take a look at this formula, as we start setting it up here, notice this is basically a fraction of the circle represented by the angle 135 degrees. It's telling us how much of the circle we're looking for. And we're going to try to figure out now how much of the circle would that be if I counted it as out of 2 pi instead of out of 360. So I write it as r over 2 pi. Now technically you could call x or something like that, but then we run the risk of forgetting that this was our radians. It's the nice thing about using r for it. We remember what our final answer is. So we have a proportion now, a fraction that is equal to a fraction. How do we solve a proportion? Cross multiply, yeah. So I'm going to cross multiply. I'm going to choose to do the 360 times r first. It doesn't actually matter, but I'm going to choose to do that first. So I'm going to do 360r equals, and now I cross multiply the other way, so I'm going to do the 135 times the 2 pi. I'm going to leave pi in there. I don't want to break out my calculator and actually plug pi into it here. The reason is because we want to keep it in exact form. And as soon as I plug pi into my calculator and get the decimal, I'm rounding it, and it's no longer exact. All right. From here, I still want to know what r is. Notice I got the 360 that's in the way. So I'm going to divide both sides now by 360. So r equals now 270 pi all over 360. We have just one last step to get our final answer. And no, it is not to calculate the actual value as a decimal. I want to leave my radian values exact. So I want to leave it with pi in there, and I want to leave it as a fraction as well. So that means reducing the fraction. So 270 over 360. I'm going to reduce that. Some of you are going to look at it and you're going to come up with the biggest number that you can divide both of them by. That's great. Do so. Some of you might take it piecemeal, like you might divide both of them by 10, making it 27 over 36, and then reduce that. That's fine as well. Whichever way you do it, though, you're going to end up with 3/4. Turns out top and bottom in this case, it was divisible both by 90. Now, 3/4 does not reduce at all. Therefore, that's my final answer. R equals 3 pi over 4. Which means that in my unit circle, if you have gone around 135 degrees, you have actually gone around the outside of that circle 3 pi over 4 units. Now, if you actually wanted to know what that was as a decimal, you can calculate it. But again, we do like to keep these things in exact form whenever possible. All right, we're now going to repeat the process here for 7 pi over 4. So, again, I'm starting with the same formula, so it's going to be something over 360 equals something over 2 pi. Full circle and full circle. In this case, the 7 pi over 4, is that degrees or radians? It is radians. Now, remember though, the pi was a big hint that it was radians, but it was not enough to know that it was radians. I know it's radians because there's no degree symbol here. That's what really told me that it was radians. So that means it goes above the 2 pi. So I'm going to write 7 pi over 4 above the 2 pi. And again, some of y'all are unhappy to see the fraction in the fraction, but it's okay. We know how to deal with it. We'll deal with it, no problem. My unknown then is d. So I go ahead and plug a d in there. All right, now we're going to cross multiply. Let's go ahead and do the easy one first. We're going to do d times 2 pi. That's just 2 pi d. All right, now we're going to be doing 360 times 7 pi over 4. Which really you could just do 360 times 7 divided by 4 and get that answer. That's fine. But I do want to show you out the long way just because I want to make sure we see why it works the way it does. So I'm going to write out the long way here. So we're going to do 360 times 7 pi over 4. The more work you show, the more you will understand what's happening. So if you ever find yourself having some confusion along the way, show more steps in your work and you'll start correcting some of that. So remember, 360 is just 360 over 1. So if I'm going to multiply it by the fraction, I multiply the 360 by 7, which is 2,520. The pi is just going to hang out up on top there the whole time through. The 4 on the bottom stays a 4 on the bottom because I didn't do anything with it yet. Then 2 pi over d. I now want to deal with the 4 that's on the bottom. So I'm going to divide that by 4. So 2,520 divided by 4 is 630. No more fraction. So 630 pi. Now, as you're going and doing these, some of you, like if you looked at this and was like, oh yeah, that's easy. I just do 360 times 7 divided by 4, and that gives me 630. Fine. You can skip these steps being shown in your work. But only if you look at it and you know immediately. If you look at it and you're like, I'm not quite sure, show more steps. It always will help. The more steps you show, the easier it is to follow your work later, and the more you'll remember. All right, we have one last step here, and that is to get the d by itself. And you'll notice that right now, we got something in the way of that. It's currently being multiplied by 2 pi, which means I want to divide to get the d by itself. Yes, I am allowed to divide both sides by 2 pi. And so, when we do that, you notice on the left side, that just leaves me with d. On the right side, we now benefit from the fact that we just left pi in there and didn't turn it into a decimal, because you notice the pi's are going to cancel each other out. So really all I have to do there is 630 divided by 2, which is 315. Now specifically though, d, remember, means degrees. If I wrote my answer like that, it looks like radians to me. I have to include the degree symbol anytime I'm getting an answer that's in degrees. So just make sure to include that with your answer there as well. Having done those, I now want you to do a little bit more practice. Now on your own. Please take each of these 2 degree measures and convert them into radians. Okay, so now go ahead and check your answer for the first one, the 30 degrees, all the work, and the final answer should just be pi over 6. And then go ahead and finish the second one, and we'll check that one here in a moment as well. All right, so having done those, we've now figured out actually a number of radian measures so far. on that table that we've been referencing back to, those spaces above the angles is where we're going to write our radian measures for our angles. And so we already know some of those then. We know 0 degrees is 0. We know 30 degrees is pi over 6, 45 degrees pi over 4, and remember the very first conversion we did was 135 degrees, which is why we know that is 3 pi over 4. And yes, we may know a few others as well. But I now want you to go ahead and fill in all of the others that you know. Your assignment for tonight is to complete the entire top of the picture with the radian measures corresponding to each one of those angles.